I think we are live, and hoping I'm audible as well. Awesome. Yeah, let me know if you guys are not able to hear me. So give a 5 star. Let's go to the coding problems. Uh, exactly. So yeah, let me know if you guys are not able to hear me or something. Right, I'll try to do something. Also, yeah, let me know how was the contest. Like whether the questions were good. Did you like the questions? Did you not like the question? Let me know about these things as well. How did the contest go? Like overall, how did the contest go? Audible. Thank you, Vishesh. Third question. Any hint? I was thinking of restaurant set, but was stuck in the end. Yes, it will be a DSU question. So we will solve the third question at the end. Like we'll go in order, like we go in the other classes. So that should, yeah. But overall, any anything that you wanted to be better or first, second, unable to solve third. Great. All right. Anyways, okay. So yeah, let's solve the problem without wasting a lot of time. So yeah, the first question tells that you are a conductor of a bus. There are n chairs and n passengers. You are given array of chairs of length n, where chairs of I is the position of the chair. You are also given the passengers array of length n, where passengers of j is the position where the jth passenger is sitting. So you may have uh, okay. So you may start with third. Uh, let's go in the order of the questions. I can start, but again, like some of them might not be able to solve like this as well. So yeah, like it will be. I think we should go from easy to hard. Okay, so is jth passenger. You may perform the following move any number of times. Increase and decrease or decrease the position of the ith passenger by 1, that is moving the ith passenger to the position x to x plus 1 or x minus 1. So basically it tells us that we have some chairs, right? We have some chairs and we have some passengers. Initially the coordinates of the chairs as well as the passengers are given. So like it is not necessary initially that the passengers are sitting in the chair. They can be anywhere. Now it is given, and what you can do is you can make a move infinite number of times. What does that tell? That tells that in a move you can choose any passenger and you can move it to plus 1 or minus 1, right? So let's say the passenger is standing at x coordinate of 2. So in a move you can move that passenger to x equals to 3 or x equals to 1, right? X equals to 3 or x equals to 1 from 2. So you can move to x plus 1 or x minus 1. You have to return the minimum number of moves required to move each passenger to a chair such that no two passengers are in the same chair. So you have to find the minimum number of moves needed to move all the passengers into chairs such that there is no two passengers sit on a chair and all the passengers are seated in some chair, right? What is the minimum number of moves possible? Note that there are multiple chairs passengers in same position at the beginning. There may be multiple chairs or passengers in the same position in the beginning. It might be true. Okay, so you are given chairs 315 and passengers you are given 274. In that case the output will be 4. That is like some of the optimal ways is some of the optimal ways can be 2. 2 can be moved to 1 by a move 1. Then 3 can be moved to 4 by a move of 1 again, so 2. And 5 can be moved to 7 by move of 2. So total moves needed is 2. 2 plus 2, that is 4. 1 plus 1 plus 2, that is 4. So the output will be 4, right? So this is the question. It's very simple. I did hash map parent by DFS, used it for PFS. Okay, so let's actually understand how do we want to solve this, right? So see, first is like we are given the list of we are given some passengers list, right? So passengers list, let's say. Now the claim here, and also we are given the list of chairs, right? So we are also given chairs. The aim is to move all the passengers to some chairs, right? So the optimal way, what I'm discussing here is the optimal way. What is the optimal strategy to move passengers to chair? See, if let's say there is a passenger of at 1 and a chair at 2, right, and there is another passenger at 2 and there is a chair at 4, right? So there are multiple ways you can arrange, right? You can move 1 to 4 and 2 remains seated at 2. Second way is you can move 1 to 2 and you can move 2 to 4. See, the number of steps needed in both of them is same, right? So 1 to 4 will be plus 3 and this is plus 0. And here it is 1 to 2 is plus 1, 2 to 4 is plus 2, that is plus 3 in it, right? So the total number of moves, it remains the same. So it is always better strategy to move a passenger to the nearest chair, right? That is, order the passengers in ascending order, order the passengers in chairs in descending order. Now map the smallest passenger, the smallest index passenger to the smallest index or the smallest position chair, the second smallest to the second smallest, the third smallest to the third smallest, and like that. And we see that the count, like even when a passenger is already seated at a chair, even if we move that passenger to a different chair, the count remains the same, the total number of moves remains the same. So we'll use this strategy to compute the minimum number of moves. Okay, so let's do that. So again, like what did we discuss? We'll move it to the nearest, we'll sort them and move it to their corresponding chairs. So sort chairs dot begin and chairs dot end, right? Similarly, we'll sort the passengers. So sort passengers dot begin and sort passengers dot end up to passengers dot end. So begin to end both will be sorted. Now int answer, int answer equals to 0, for int I equals to 0, I less than chairs dot size I plus plus, answer plus equals to what? ABS of chairs of I minus passengers of I. So the ith passenger goes to the ith chair after sorting. So whatever is the absolute difference, that is the amount of distance he has to cover. So that should be it, and finally return answer, right? So let's run this code and let's submit this. So this is working, right? This was a pretty easy problem. I think everyone must have solved this, but again, if you didn't, this is the strategy. Like we find that, hey, even if we it's always better, it's always in our best interest to move a passenger to a near to sort the passengers and the chairs and map them accordingly. That gives the same result as even like in case you don't have to move some passenger and then map it, like map a different passenger to a different seat, right? So this is always the optimal possibility. Okay, so let's go to the second problem. I see many of you are already discussing about the second problem, so I think this should help. I'll be able to help in some way here. So let's read the second problem. So Chota Bhim wants to eat the maximum number of laddus in Dholakpur on an Independence Day. The houses in Dholakpur are arranged in the form of a binary tree and have laddus same as their house number. Chota Bhim is standing in his home initially. Find the maximum number of laddus he can eat if he can go to the houses at a maximum distance of k from his house, right? So he can go to a maximum distance of k from his house. What is the maximum number of laddus he can eat? The number of laddus at his home should also be included in the sum. Every house has distinct laddus in it. So for example, we are given a tree here, that is the first house has number of laddus 1, then 2, 9, 4, 5, 7, 8, 19, 20, 11, 30, 40, 50. And the house number is same as the laddu number of laddus. So now home is 9 initially. So the home is 9 and k equals to 1. That means Chota Bhim can travel only up to a distance of 1 from his home, right? So what are the nodes at a distance of 1? 5, 7 and 1. So he can only travel and these nodes and can have laddus. So what is the maximum number of laddus he can have? 9 plus 1 10 plus 7 17 plus 5 22. So the total number of laddus he can have is 22, right? Similarly here k is 2 and initially 40 is the starting node, right? So for from 40, what are the nodes at a distance of 2? So eventually the question reduces down to what are the nodes at a distance of 2 from 40, right? So from 40 the nodes at a distance of 2 will be 19 54. See, from 40 we can go from 9 to 19, it is at distance 1, 50 is at distance 2, 4 is at distance of 2, and any other node 8 is a distance of 3, right? Similarly 2 is a distance of 3. So only these nodes are at a distance of 2, so he can only visit these nodes and the total amount of laddus he can have is 113. Okay, so this is the question, how do we want to solve it? Now I see many of you are telling that hey, we can convert it to adjacency list and do it. Yes, you can do it. Like that might be one of the solutions. Although I don't know if that should pass the constraints as well. Like you can create a tree. So this is actually a very simple problem if you have an adjacency list given to you, right? If you have the adjacency list given to you, it is just starting your DFS from 40 and going up to like at a distance of 2 units, right? Nothing else. So running a DFS of distance of the height 2 from some node, as simple as that. So if you are constructing the adjacency list and then solving this problem, it should be very straightforward, right? It should be very straightforward. Just like create the adjacency list, start your DFS from 40 and go up to a distance of k units, right? Store that as a height parameter. So that should be it. But again, like we'll not try to recreate the tree, we'll try to use the tree that is given to us and find out a better solution, find out another way to do this, right? Maybe not a better solution, but how to do it without reconstructing the tree again, right? So here one thing to note, that we are only given left and right pointers, right? We are only given left and right pointers. That means we cannot go back to the parents, right? And in our answer we have to go back to the parents, but we are not given that, right? So definitely we have to rely on the recursion. We have to somehow do the recursion so that we can pass, like unless we want to reconstruct the tree again. If we want to reconstruct the tree, if we want to store parent as well, like we want to store parent as well for a node, or we want to create an adjacency list, that's a different way, and that's a much easier way to solve this problem. Like definitely you can create an adjacency list quickly out of this tree and run a DFS, right? That's a much easier way. But without reconstructing the tree, if we want to do this, we do not have the information of the parent for a given node, right? So we cannot travel to the parent. In that case, what we have to do is we have to rely on recursion. That is, we have to find we have to do a recursion such that is when we do a DFS, we have to somehow convey this information to the parent, that or to our ancestor, that hey, we have found the node and it is at a distance of this much, right? Okay, so it is at a distance of this much. So let's understand this question properly. Let's quickly write down this tree. Take my writing pad. Okay, so we have 1 2 what was there, 1 2, let's see again, 129457, 129457. So it should be 129457. Astadu, just wait for some more time. Let us solve this question and then we'll move to the third one. 975 5 is done. 8 9 20 11. 8 9 20 11. Let's go up to 8 9 20 11 only, right? 8 9 20 11, something like this, right? Okay, so we are starting from 9. This is our home, right? This is our home. So again, like we start the DFS from here. So in the DFS, when we do the DFS, somehow when we reach 9 and we come back to 1, we have to convey 1 that hey, we have found 9 in the right subtree. What do we want to convey to 1? Just understand, what do we want to tell 1? We want to tell 1 that hey, we have found 9 in the right subtree. So these are important, right? You have to understand what you need to pass to 1. We have found 9 in the right subtree at a distance of 1. So we have it's 19, not 9. Okay, is it 19? I can see. Maybe. Where is it 19? Okay, bottom one, 19. Okay, sorry. Yeah, it should be 19. This is 19. Anyways, this is not relevant in our case, but yeah. So at a distance of 1, we have to convey this information. So what are the two keywords that are important here? Right subtree. First is we have to convey to 1 that it is in the right subtree. Second is we have to convey to 1 that it is at a distance of 1. Okay, cool. How do we convey about right subtree? How do we convey about right subtree? It is actually pretty simple. If we run a DFS, like when we run the DFS, how do we do? DFS current node, let's say current node is stored in current. We do like this: current of left, then DFS current of right. So see, whenever you are solving a tree problem, if it is involving a binary tree or any NRE tree, and you understand that you have to use a DFS, half of the problem is solved just by identifying what is the thing that you need, right? In our case, we needed, like, for the subtree of 9, it is very easy to compute what are the sum of the nodes at a distance of 1. For a subtree, it is very easy to compute. What is not easy to compute is outside the subtree, that is this part, right? This part, what is the, like, this remaining part, right? What is the sum of the nodes, right? This part is the difficult part. So if you break down the problem like this, that hey, at any node we want to find if the target node is at the left subtree or at the right subtree or nowhere, and it is at a distance, what is the distance it is from, right? So that is what we need. So now the first thing we realize here that we do the DFS independently, right? We do a DFS independently. So if we maintain some kind of, like, called a, let's say, a flag or something like that, let's say we set the flag to false, right? We set the flag to false. We'll not use a flag exactly, but we set the flag to false. And if we visit the node, right, if we visit the node, so if current equals to if current of data is equals to home, that is the condition, right, for the node. So in that case, we'll set the flag to will return true or something like this, right? Return true, something like this. So now when we do DFS current of left, so let's consider 1, right? When we do DFS current of left from 1, we get false because 9 is not there in the left subtree, so we get a false. When we do DFS current of right from 1, we get a true back, right? Because 9 is there. So the first case is easy, but just by having some identified, just by sending some value, we can identify whether 9 is in the left subtree or in the right subtree, or it is not there. So the first part is very easy, right subtree, because we can leverage the recursion in that. Now let's talk about the second part, which is the more challenging one, right? How do we tell what is the distance? So now instead of flag, what we can do is, instead of sending a flag of true and false, we can actually send the distance, right? So if the distance is greater than equal to 0, then it is a valid one, like the remaining distance, right? Not exact the distance, but what is the remaining distance, like what is the remaining nodes we can cover, right? After this node, what is the remaining amount of nodes that we cover? That is what we want to send. So let's make it a bit simpler, right? Let's for now send what is the distance of the node from the given node, right? So when we reach k, when target equals to k, right? When target equals to k, we can return the height of the node. We can maintain the height in the DFS as a DFS property, like DFS, let's say we are at current node and we have a height, right? We can maintain this as a property. So we can return the height of the node, and at the given node, when we call DFS left or DFS right, like let's say for 1, when we call DFS right, we get the height to be 2. The height of this node is 2, right? So we get the height to be 2. We can subtract it from 1, that is the height of 1, that is 1, that is equals to 1. So we know that this node is a distance of 1, is at a distance of 1 from 9, right? So we can know this about this. So the second thing also it comes from this, that the way we send, what value we want to send, if we want to send the distance, right? If we want to send the distance of how deep or how far is the target node from the current node, that information can also help, right? So that's about it, right? So that's about it. Now how do we leverage these two things to compute our answer? Let's understand that, right? How do we leverage these two things to compute our answer? Okay, let's do a dry run on this to understand our algorithm, right? So what we'll do is, our algorithm will be something like, if it will return, now it is a int dfs, right? It is not a void dfs anymore, it is a int dfs. So let's write in white only. So int dfs, right? In dfs, what does it tell? It tells us what is the number of nodes it will return. If what it will return is, what is the number of nodes remaining from this point, right? What is the number of nodes we can visit more from after this, like after returning from this, right? So for example, 9 will return. After 9, when we reach back to 1, just think about it, when we reach back to 1, what is the minimum, what is, so 9 will return to 1 only, right? 9 will be returning to 1. When 9 returns to 1, it will return what is the more distance of nodes that we can cover from 1. So it should return 0, right? Because from 1 we cannot cover any other node, so it should return 0. So that means we'll just end up at 1. And let's say it returns 1, right? So that means from 1 we can cover a distance of 1 more, right? That is, we can go to this 2 as well. Okay, so let's understand this. Let's say k equals to 2 in our case, right? Let's say k equals to 2 in our case. So let's understand this for k equals to 2, because that will make it much more sense. So okay, so when we reach 9, for 9, when we reach target, right, this node, first of all it goes to the left subtree, and it doesn't find anything. So it will return -1. Let's say it returns a delimiter called -1. So we know that the target node is not on the left subtree. Now we go to the right subtree. In right subtree we find the target node. Once we find the target node, we will stop our dfs there. But what we want to do is, we want to compute the nodes at a distance of 2 from 9. Nodes at a distance of 2 from 9, that is the sum of these nodes, right? So we'll just do another dfs for the depth, and we'll compute this sum, right? We will compute this sum, that is 5 plus 7 plus 20 plus 11 and plus 9 as well. 9 will also be included because it is at a distance of 2. So for the subtree it's simple, right? We'll just do a simple dfs from 9. For the subtree it's simple. Outside the subtree, what will now send? We'll send k minus 1 from here, right? K minus 1, that is outside of 9, it returns to 1, right? From 1 we can visit a distance of k minus 1, that is 1 more. K minus 1, k is 2 right now, k minus 1 is 1, that is from 1 we can visit a distance of 1 more, and those will also be included. Chota Bhim can visit a distance from 1 from 1 unit more, and those will also be covered. So 1 in which direction? In the left side, because on the right side we have already computed. So in the left side you can visit at a distance of 1. So we'll just go to 2 and we'll add it to the sum. So plus 2 will be there, like this is at a distance of 1. Again we'll do a dfs from 1. Now it will again send back to its parent, right? Now it doesn't have a parent node for it, but it will again send back to its parent, because from the parent it will be again distance -1, that is 0. It will tell that from the parent, let's say there was another parent node here p, it will tell from the parent that it can visit 0 more nodes. That is, it cannot visit any other nodes from parent, but it can visit the parent itself. So we'll have to add its answer as well. For example, if k was 3, in that case from 1 also you could have gone up, right? From parent you could have gone to more nodes, like something like this, right? So that information has to also be conveyed. So again, what are the directions in which we want to send the answer? First is whenever it matches the target. Let's say this is 9 and target is also 9. Whenever this matches, you will compute the sum of the subtree of distance k, right? You will send what is the number of nodes you can visit more from this node, right? From the previous node. That is, you will send it to its parent p, and you will send a value k minus 1. That is, from p you can visit k minus 1 more nodes. Why k minus 1 again? Because 1 is already covered here. 1 is already covered here, and k minus 1 more nodes you can visit from p. So k minus 1 more distance you can visit from p. So for the child nodes, you will compute like what are the nodes at a distance of k minus 1, right? You will find their sum, and also on top from parent, when it goes away, it will be k minus 2, right? Because from the parent, let's say k equals to 3. So for 3, you know that here it will be k minus 1, that is 2. From this parent, you can travel 2 more places. You can travel 2 more places. On the subtree will do. And outside the subtree, you can travel 1 more place from the parent, right? From this parent, you can travel 1 more place, because 3 more places. So 1, 2, and let's say there is another node, so 3. It makes a distance of 3, right? So that should be how we can do it, right? Again, like, it might seem a bit complicated, but if you, like, explanation is complicated, but if you see the code, it will be pretty simple, right? So let's write the code, and again, like, if you don't understand, I'll try to explain again. That should be okay. So yeah, first thing, we want to compute the sum. So let's maintain this variable int sum equals to 0, or int sum, right? And also let's maintain the variable what is the target. Okay, this is the target. Now we want to do one thing, that is int dfs. In dfs, because it returns what is the distance you can travel more from here, and we are at a node, at some node current, right? We are at a node current. And also let's add k here as well, or we can add k as a variable as well here as well. Okay, int k, what we can do here is, okay, node current and k. Now if current equals to null, just return -1 from here, because this is not valid. Okay, current equals to null, so return -1. Now if current of data is equals to the target, that is, we have found the node, right? Target. So we will have one more method called calculate subtree sum. So void calc subtree sum, and it will take some node current and in distance. Rather, it will not be calc subtree sum, rather it should be calc subtree sum for given depth. Okay, so calculate subtree sum for given depth. So given a depth, right? Let's call it a depth, right? Given a depth in the subtree of current, what is the sum of elements up to that depth, right? That is what we want to maintain. So what is the sum of elements up to that depth? So let's actually write it quickly. So if depth is equals to 0, so in that case you have already gone to the maximum depth, so you can return. Or if current is null, that is, you have reached to a null node and the depth is not yet over, so in that case you have to return. Otherwise you can add it to the sum. So sum plus equals to, let's write it like this, dot sum. This sum plus equals to current of data, and now we can call calculate subtree sum for given depth, current of left, and depth is reduced by 1, depth -1. Similarly, calc subtree sum for given depth, will call for the right subtree, current of right, and depth -1. So the subtree sum is added. For current, the subtree sum up to a depth of depth is added to this sum, right? So that is done. So current of data equals to target. If we reach the target node, what we want to find first is the subtree sum at a distance of k, right? So subtree sum, that is, we'll call calculate subtree sum, calc subtree sum for given depth. So from the current node, we'll go up to a depth of k, right? So the current node is at depth of 1, and we can go up to get depth of k. So we'll add all their values, and then we will return k -1. Why do we return k -1? Because from the parent, what do we want to know? From the given node, how many nodes we can visit more. So from the parent node, we can visit k -1 nodes more, right? So k -1. Okay. Now, first thing is, right, int depth or int distance, let's call it distance, equals to, first we'll call dfs for the left subtree, current of left and k. Now if distance is not equals to is greater than -1, if distance is greater than -1, in that case it is in left subtree. that is the target node is in left subtree, in that case we will calculate, first of all we'll add this to the sum. So sum, this sum plus equals to current nodes of data sum, and then we'll calculate subtree sum, calculate subtree sum for given depth. Calculate subtree sum for given depth up to what depth? Current. For current of, we have found it in the left subtree, so in the right subtree we have to include it. So current of right and depth will be depth minus 1, distance minus 1. Why distance minus 1 again? Because 1 unit again you are removing from going to current of right. So you have covered one more distance, so distance minus 1. Okay, and return distance minus 1 to its parent, right? To its parent return distance minus 1. Similarly again distance equals to dfs current of right and k. Again, like if it is not greater than minus 1, if distance is greater than minus 1, in that case it is in right subtree, it is in right subtree. So this dot sum plus equals to current of data, this will definitely be included because distance is greater than minus 1. Now we'll also check if we can include some subtree sum as well from the left subtree. So calculate subtree sum for given depth. We have found in the right subtree, so we haven't included the left subtree yet, so let's just include it. Left, calculate left and distance minus 1 and return distance minus 1. And finally if both of them are not true, so it is not present, so it will return minus 1. So that should be the entire code. So here we can initialize a few things. This dot target equals to home, this dot sum equals to 0, return this dot sum, and we will compute dfs root and k, will pass this. So that should be the code. Okay, we are getting 162.3. That's weird. It should not give. Come on. Current equals to null. Return minus 1. Current of data equals to target. Okay, let's again walk through the code. By the way, why we are returning k minus 1? Just think, where will this value be returned? Where will this value be returned? It will be returned when from the parent we call, let's, for in our case, in our example. So in our example, let's take this example, right? When we reach 9, it will send the value to whom? 1. When this was called, dfs current of right comma k was called. In this we want to tell to 1 that from 1 we can visit a distance of 0 more. We can visit a distance of 0 more. That is, see here we are again, like as it is greater than minus 1, it will return k minus 1, that is 0 to 1. So as the distance is greater than minus 1, the sum will be added here. But calculate sum subtree for given depth, current of left and distance minus 1. Distance minus 1 becomes 0. Distance minus 1 becomes, it doesn't become 0, it becomes minus 1. So it is less than 0. If it is less than 0, in that case. So it becomes less than 0. So this doesn't add anything. It goes to here directly and it returns. So it doesn't add anything. That means we will not include the left subtree of 1. Will not include because the distance here is becoming 0. So let's compile and run right now. I think that was a mistake. Depth less than 0 it should be. Yep, 22 is correct. So let's submit this. So this is also working. Is this clear with everyone? Like, what is this DFS returning? It is returning from the given node how much more you can travel, how much more you can travel to the other, or like to the top or to the other subtree. That is, when you call this thing, right? Just think about this. When you call this thing current of right, let's say it returns a value 2. It returns a value 2. That is DFS current of right from the current node returns a value 2. It means that from the current node, we can move a distance of 2 more, either on the left subtree or on the top, right? Either on the left subtree or on the top. So that's why when we call the calculate sum subtree for the left subtree, we pass distance minus 1. That is, we can move a distance of 2 more. that is 1 and 0, right? 1 and 0, that's why we do -1, and then we return dist -1 again, because from the top, if we go one more step, again we have reduced the step by 1, like we have taken one more step, right? So we can travel a distance of 1 less again, so distance -1. So again its parent will also receive something like this, distance -1, and it will calculate again from the left subtree or the right subtree and towards its parent, so something like that, right? So this is the code. Again, like, the only trick here was how do you identify, uh, like how do you identify what is the data that you need, right? What is the data that you need at every node? So at the parent node, we just needed how much distance it is and which side it is on. So both the things we are getting from this DFS, like current of left, that time we are checking if it is on the left subtree or on the right subtree. Both of them will not be true at any point of time. One of them will be true. So we are checking that and returning based on that. Okay. Uh, Cases have got passed, right? Cases got passed. Okay. So again, like, just let me quickly reiterate. Mohammed didn't understand it, so let's reiterate quickly. So first thing, current is null, then return -1. Simple. If it is equals to target, again, like we have this method. What does this method do? Let's write it down here. What does this method do? It calculate subtree sum up to given depth, and we don't want to calculate only the sum, rather we want to add it to the final sum. So we are just directly adding it to the final sum, right? So calculate the subtree sum up to given depth, right? So that was one. Now if current of data equals to target, right, if it is equals to target, then we are just calculating the subtree sum up to a depth of k. We are just calculating the subtree sum up to a depth of k, right? So that's what we are doing, because we can travel a distance of k, right, in the subtree as well. So directly we pass k. And why k? Because the current node is also included. We are starting from the current node, so the current node is at a depth of 0, so we can go at a depth of k more, right? So that's why k, and we'll return k -1. Now this is important. Why do we return k -1 here? Just think about it. Where is this value returned to? And secondly, what does this DFS returns? DFS, it will returns how much distance the parent node, how much distance the parent node of the current node, how much distance from the parent node of the current node can beam cover. So it tells us how much distance from the parent node of the current node can beam cover. So this DFS was called by some parent node. Now we return k -1, that is at the parent node. From the parent node, beam can cover k -1 distance more. When k equals to 1, let's say in our case the k was equals to 1. So from the parent node was here 1. From the parent node, beam can cover a distance of 0 more. That is, he has to stay at this node. He cannot go to 2. That is what this returns. So k -1 will return how much distance. So k from the home node. So from the parent node, it should be k -1, because one distance is covered here. So it will be k -1. And now here we'll call DFS current of left. First of all, we'll see current of left, what it returns. If it returns something that is greater than -1, that it has the node. So it means that the left subtree has the home node or has the target node, home node. In that case, we'll add it to the first, and it is also within the distance of k. Not only it has the home node, it is also at the distance of k. So we'll add it to the current sum. Then for the left subtree, let's say we have found it on the left subtree. So on the right subtree, we can cover a distance of distance -1 more. So we will calculate the subtree sum up to for distance -1 depth, and we'll return distance -1 to the parent. Because again, one distance is covered between the parent and its parent. So that much is covered. Again, we'll do the same thing from the right child, and in this case, we'll go to the left child up for distance -1 depth, and will return distance -1 to the parent, or finally we'll return -1. So that should be the logic. I hope it's clear with everyone now, and if it's not, please rewatch again. Cool. Let's go to the last problem, right? Let's go to the last problem, and this is where I think all of you were interested. Okay, so let's understand the problem. This, because I also believe, again, I also believe this question, the problem statement was not very proper. It could have been made a bit proper, but again, like, if you just tried understanding it a bit, it should have been clear. But again, like, I would definitely agree that the problem statement could have been a bit clearer, right? I would definitely agree to that. So let's read the problem statement. Geek is a chemical scientist who is performing an experiment to find an antidote to a poison. The experiment involves mixing some solutions in the flask. Based on the theoretical research Geek has done, he came up with an n into 2 array mix where mix I is equals to xy denotes solutions x and y needs to be mixed. Also, from his past experience, it has been known that mixing some solution leads to an explosion and thereby completely ruining the experiment. The explosion solution is also provided with a m into 2 array danger, where danger of I is equals to pq. Denotes that if somehow solutions p and q get into the same flask, it will result in an explosion. Help Geek determining the answer of size n, where the answer of I is yes if it is safe to mix the solution and no otherwise. Also, this note was very important. This will give a lot of context. Geek should follow the order of mixing of solutions as it is in mix, otherwise the antidote will be ineffective. So he should process them in order. Also, Geek will not mix the solutions in mix I once he gets to know that mixing them will result in an explosion. So if there is a in the mix, there is a formula where you are mixing two compounds, and if you know that it will cause an explosion, you will not be mixing them. So that is the question. Okay, now the test cases that are given are pretty weak, right? The test cases that are given, I agree, these are pretty weak. So we will actually go with a better example, right? We'll try to form a better example. Okay. Sorry. Anyways, let's actually understand this. Okay, let's take an example. Let's say there are maybe 5 10 compounds, or not 10, maybe 10 compounds. Let's assume 10 compounds. First of all, we mix 1 2, then we mix 3 4, then we mix uh, then we mix 1 4, right? Then we mix, sorry, 1 5. Let's say we mix 1 5, then we mix then we mix 2, then we mix 2 5, let's say 2 1 5, then we mix 2 3, and then we mix 2 5, right? So in this case, what will happen exactly? Let's see. Firstly, and let's say there's a danger array. In danger array, we have that, hey, if we mix 3 and 2 together, it will cause an explosion. Or rather, not 3 and 2, let's say it is, if we mix 5 and 4, 5 and 4 together, it will cause an explosion. This is the danger array, right? 5 and 4 will cause an explosion. So let's understand. See, 1 and 2 are mixed initially. This can be done, right? 1 and 2 will not cause an explosion. So you will mix 1 and 2 together. 1 2 come to the same set. Now you are mixing 3 4. 3 4 will not cause an explosion. So 3 and 4 comes to the second set. 1 and 5 are mixed. So now 1 and 5 also doesn't cause an explosion, right? So 1 to 5, they come under the same set. This is important. 1 to 5, they come under the same set. Like, you are actually creating the antidote, right? So you are actually mixing items. If you, it's not like you are just mixing 1 and 5. 1 and 2 has already been mixed. So when you are mixing 1 and 5, 1 to 5 will form a solution. 1 to 5 will form a solution. 2 and 3 are mixed. Okay, now 2 and 3, here come to this, 2 and 3, we are trying to mix 2 and 3. 2 already is in a solution with 1 to 5, so you are mixing 1 to 5 with a solution where there is 3 and 4, and we see that there is an explosion between 5 and 4. There is an explosion possibility between 5 and 4, so we will not do this mixture. This mixture will cause an explosion, and that was the important thing. So most of you, like whatever you have done, you are treating each of them independently, right? Whether 3 and 4 is there in the danger set, whether 1 and 5 is there in the danger set, that's not exactly the question. When you are mixing, they already are mixed. 1 and 2 are already mixed. So when you mix 1 and 5, 1 and 2 already has formed a solution. So you mix 5 to this. So basically your solution now has 1 to 5. Now when you mix this with 3, when you mix 2 and 3, basically you are mixing these two solutions. And 5 and 4 will cause a reaction and it will cause explosion. So you cannot mix them, right? Now we'll continue 2 5. 2 5 will work. 2 5 will not cause an explosion. So we'll continue with this one. We'll just skip this one. We'll assume that this one didn't happen. Make sure to exclude this, like this one should not have happened, right? So that was the question. Now how do we solve this? Again, very simple. Once you get the concept, it is very simple. We are having disjoint sets. We are having disjoint sets. If a reaction is successful, or mixing is successful, we are kind of merging two sets, disjoint sets. We are merging two disjoint sets. Otherwise, to check if reaction will be, to check for explosion, we see that their representatives, or that their representatives, let's call it, their representatives do not cause an explosion. Okay. Map pair intent will not work, again for the same reason. It's not like you are telling that, hey, first do 1 2, then do 2 3, then do 2 4, like this. Not like this. You are telling that when you are doing 1 2 and then you are doing 2 3, it means that 1 2 3 come together in the same solution. Then when you mix 2 4, it means that 1 2 3 4 come together in the same solution. This is not something that you're accounting for. You are treating each of them independently. It's not happening independently. You are mixing to the solution, right? You are mixing to the solution. So this is not happening independently, and that's why you need to do a DSU here, a disjoint set union here, right? So this can be solved using a DSU, disjoint set union, right? And it's pretty simple now. It has reduced very simply. Like what you can do is, let's say the DSU exposes two methods. Like DSU will have two methods. One is find root, one is combine, right? Find root and combine if both elements fall in both sets. Okay. So find root, again, how to do this? Let's understand the intuition completely. So first of all, when you get a reaction, right? When you get a reaction, what you can check is, first of all, you find the representatives. Like what? So every set will be represented by one element, right? That is the concept of DSU. Every set is represented by one element R, right? So first of all, you will do that. That is the root element. DSU dot find root. DSU dot find root of U. DSU dot find root of V. So that is RU and RV. Let's call them RU and RV, right? So if RU and RV are in the same thing, RU and RV are in the same thing, you can just continue. Like they have already been merged, so it's okay. Otherwise, and also the answer for this will be yes. Otherwise, you can go through all the elements in the blocked list. So for blocked element belonging to the blocked list or danger list, you go through all the elements in the danger list. you find their corresponding representative elements as well, like whether they have formed a set or they are independent, you find their representative elements as well. So let's call them Rx and Ry. Rx equals to find root of u, and again find root of this, find root Ry. Then you check if Rx equals to or the mean max, like that, something Rx equals to Ru and Ry equals to Rv. That means you are actually combining two sets. You have two sets represented by Ru and Rv. You are combining two sets in which there is at least one compound in each of them that will react together and make an explosion, right? So this is how we can do. So finally, once you have determined that, you can decide whether to, like, if it is a successful reaction, then you can combine, then you can call DSU dot combine between them because it is a successful reaction, and you can combine them RV. Otherwise you will not combine them if it leads to explosion. Okay, what is meant by DSU? Please read about it. I'll not explain like what a DSU is, but again, it's a data structure that whenever you have problems, like you have disjoint, you have multiple disjoint sets, you have to unify them, or you have to find the candidate, like if they belong to the same set or not. In those cases, it is a data structure that helps with that. Okay, so let's write the code for this. First of all, let's write the code for DSU. Class DSU, and here we'll have the vector int parent. So we'll just use path compression, vector int parent, so public, and here we'll have the constructor DSU int n, parent equals to vector int n, and for int I equals to 0, I less than equal to n, in fact it will be n plus 1, I less than equal to n, I plus plus. Initially each node is a parent of itself, so parent of I equals to I, right? Now we will have the find root method, int find root int x. For node x we want to find the root, so while x not equals to parent of x, we'll do a path compression here. Parent of x is equals to parent of x, and x equals to parent of x. Again, like these are very specific to DSU. Read about, if you don't know about DSU, read about it. Read about path compression, union by rank, and these things. And void combine, we are combining two nodes u and v, and int ru equals to find root of u, int rv equals to find root of v. If ru equals to rv, return. Otherwise parent of ru equals to rv and return. Parent of ru equals to rv and return finally. So that should be it. Now let's write the code for this. So here we have, okay, so DSU equals to new DSU, so DSU equals to of n, size n. Now here what we want to do is for int I equals to 0, I less than n, I plus plus. So first thing we want to do is ru is equals to find root of mix of I0, DSU dot equals to DSU dot find root mix of I1. Now we'll make a boolean variable, bool does explode, right? Does explode equals to false. So for int j equals to 0, we'll go through all the elements in the danger list, j less than m, j plus plus. Okay, int d danger x, let's call it dx, is equals to dsu, like we'll find the sets in which they are, dx is equals to root find root okay, dx equals to find root of mix, sorry, danger I0, and in dy equals to dsu dot find root danger I1. Now we will check if any of them causes an explosion. So if max of ru comma rv is equals to max of dx comma dy, and min of ru comma rv is equals to min of dx comma dy. So basically what is this logic exactly? This is just telling, this is just comparing, this is how you can compare between if two elements are same. ru rv is equals to dx dy. This is how you compare. Max of them should be equal, min of them should be equal. So if both of them are equal, in that case does explode is true. If does explode, also we need to store the answer. So vector string answer of size n, answer of I is equals to no, and continue, else answer of I is equals to yes, it doesn't explode. We will combine now as well. So dsu dot combine mix I0 mix I1, we are combining these two things, and yeah, dsu dot combine, that should be it. So combine, and finally we can return the answer array. So return answer array. So let's compile and run this. We have some segmentation fault. Let's quickly check. J equals to, okay, this should be j0 j1, my bad. So let's run this now. Yes, no, this is working. Let's try to submit. Its time limit exceeded. Interesting. The DSU is slow, will explode. J equals to 0, j less than m. Let's also do union by rank as well, so that it reduces the complexity of it. So vector in subtree size, and here it should be subtree, okay, parent of I, this thing, and subtree size equals to vector int n plus 1, and subtree size of I equals to 1, and here return, and if subtree size of ru is greater than subtree size of rv, small to large, so rv will be merged to ru, parent of rv equals to ru, and subtree size of ru plus equals to subtree size of rv, else parent of ru is equals to rv, and subtree size of rv plus equals to subtree size of ru. So this is small to large, that is union by rank plus path compression. So that should be it. Dx dy does explode, that should be okay. Yeah, this should be so. And also, like, if you can see the constraints as well quickly, everything is 1000, so 1000 into 1000 should work fine. Let's run this. Okay, this is working. Let's submit. It's somehow giving me TLE. Is it one based or zero based? One based, it is one based, so that should be okay. J equals to 0, j less than m, j plus plus, we find their root. Does explode is true, does explode answer equals to no, else answer I equals to yes, and we combine. In combine we use union by we use path compression, so that should be fine. And yeah, this should be fine, unless, okay, let's just move these things out, right? Sometimes basically interacting with the classes actually take time, although it's a good pattern, but again, like, it will take time. So we can just do something like this: vector int, and somewhere here we'll write these two statements. That should be it. So we get rid of this thing, and yeah, like that should be. And dsu dot will also not be there anymore. So find root mix of I0, find root mix of I1. And here we can add one more step, that if ru is equals to rv, then we can just make answer of I equals to yes, and then continue, just simply, right? So that should be it. And here also, when we combine, we can combine directly between ru and rv. We already know the roots, so we don't have to waste a lot of time here as well. So does explode, that should be there. It should be just combine, and it should be just find root, find root, find root, find root. That should be there. Okay, so let's run this code. So this is working, let's submit. And I think it's going for time limit only. Oh, it's going for time limit again. uh Anything else we can do? Parent equals to vector int n plus 1, subtree size equals to vector int n plus 1. Parent of I equals to I, subtree size is 1 initially. Answer, going through all the elements, find root, find root of mix of I1. Here we are doing path completion as well. Sorry, go back to, in fact, we can make this a bit better. Like, instead of this, what we can do is, instead of this, what we can do is, if x equals to parent of x, return x, else parent of x equals to find root of parent of x, and return parent of x equals to find root of parent of x, and return parent of x. Find the root and return parent of x, directly combine. This is also a type of path completion. We directly go to that one. So that let's see, that actually still get the answer properly. Answer I equals to yes, does explode is false. It's taking more time. I'm not, why is it taking more time? Answer of n, explode is true. Answer of I equals to no. Answer of I equals to yes, and combine. Also we can break here as well. So that's one optimization that we can. We don't have to travel fully, we can break here as well once we get through. Yeah, that's also. So basically it just it's pretty stupid. But again, the time complexity should have been adjusted. But again, like we should, whenever we find something is exploding, we should break immediately. There's no point of continuing. So yeah, that should be it. So yeah, like we have solved all the problems. I hope that this was also clear with you guys, that basically, although the question might not be a bit clear, but again, like it suggests that hey, just make the mixture, whatever is in the mixture, you combine between them, right? You don't take new samples and then combine. Okay. So any questions? Any questions? This, or otherwise we are done with the class. If you have any questions. So if you don't have any questions, I think yeah, like we are done with the class. So thank you guys for joining in, and yeah, I'll be